So now comes the next important object, which is when I say, I need a notion of how important things are. What I mean by that is a notion how important they are for what I care about. So I have to tell you, what am I measuring? I might care about the temperature in Chicago, I might care about pressure, or I might care about something else, but I have to tell you what is it I want to measure, because then you can tell me how good is the measurement, what are the errors in various approximations, etc. So a perfect example is, if you're interested in Professor Goldman, then this event will be a very high probability event. So we'll produce an observable that says we've heard Professor Goldman. Now this is a rare event in terms of our class, because this happens once or twice per lecture, whereas you hear Professor Cvitanovic drone on all the time. So you would design an observable, which would be called a Goldman observable, and we'll give it some name, AX. And it says how likely, well, in this case, it's a state observable, but we will try to think about it. Well, we'll discuss time as well, which is, how likely I am to hear Professor Goldman. Now, that observable is somewhat low at my house in Virginia Highlands, though not zero, strictly. And, it's very high on the second floor on this classroom, etc. So there'll be some observable, which will be the measurement that I care about. The word you have probably heard in quantum mechanics only so far. I hope it's not confusing. It has the same meaning as in quantum mechanics. For example, if spin is an observable, I measure it's up or down. And if this chalk being up or down is an observable, I'll measure likelihood of that. So the moment we have an observable, we can talk about averages of observables. And that's a necessity in chaotic dynamics, because we'll be unable to predict what happens to long time to any specific initial condition. We'll only be able to make predictions over averages. Again, there's no statistical mechanics in this. This is deterministic. We'll give you a rule how to compute this observable, but of necessity. And it'll depend on what density function I use. So average, space average, will be integral of this observable weighted by the likelihood I'm in point x over the space. And just to make sure, I will divide it by density of m, just in case I'm looking at subspace or the whole space or whatever. I'll divide it by integral, or the total mass. That's just a normalization. So if observable is 1, everything is equally important to me, then I'll give the 1 back. So any average of 1 will be 1. So this is mass. Usually I just normalize it so it's 1 already, but just in case you didn't. And if this thing, we'll call this average rho without any indices. If we use the natural measure, rho 0, whatever. If this is natural measure, then we'll just call this a space average of rho without any subscript, because that'll be a case of interest.